alkene compounds can undergo catalytic hydrogenation reduction. This is basically in the presence of palladium, which is a transition metal, with carbon. Palladium carbon or palladium charcoal here as a solid catalyst. The other reactants will be hydrogen gas. If you pass hydrogen gas into a compound with double bond in the presence of a palladium carbon catalyst, you can saturate this double bond with hydrogens. So it basically looks like adding the two hydrogen atoms onto two carbons on the double bond. So it looks like one hydrogen will be added to one carbon, the other hydrogen will be added to the other carbon. This applies to linear alkenes or cycloalkenes. The mechanism of this reaction is for understanding purpose only. So basically, this bar represents the palladium carbon surface, solid surface. When the hydrogen gas passed on it, it will generate two separate hydrogen atoms, and these two hydrogen atoms will be added towards the double bond at the same time, which is so-called a syn addition. Syn addition meaning two hydrogens will adding towards the double bond at the same time from the same direction, same side. So if you look at cyclopentene as an example, you will find these two hydrogens are going to be added towards the same side of this double bond carbon. And of course, after the addition, you're converting a double bond into a single bond. Now this reaction is fairly straightforward. As you can see, just remove the double bond. You don't have to show the hydrogens, but you have to understand there are actually additional hydrogen on each carbon here. One of the applications of this reaction is that we can use this reaction to determine the relative stability of the alkene. Now you can see with three different alkenes on the left side, we're going to undergo the same addition to hydrogen gas. We're going to result into the same products. Now since they are all the same products, these three compounds, so they all have the same energy. And if we measure the enthalpy change of this reaction, you will find from different alkenes to the same products, we're going to release different amount of heat. For example, if you're coming from the bottom one, we release the most amount of heat compared to the ones at the top, which means the ones at the bottom relatively have a higher energy than the ones on top. Now with higher energy, that basically means it has a lower stability. Now using this method, we can determine the relative stability of alkenes or relative stability of double bonds. Now here's the conclusion. So basically on any alkene or double bond, the more alkyl group bonded to the sp2 carbons, the more stable the alkene will be. So for example, if you have a double bond or alkene double bond with 4 alkyl substances, 2 on each, they don't have to be the same, but they have the alkyl groups. That will be the most stable. And if you have one less alkyl substance or you have one hydrogen substance on it, they'll be a little bit less stable than the previous one. And this goes down the road when you have more hydrogens, less substance, all the way to if you have no substance or one substance, that will be the least stable one. So the number of substances on these two carbons or alkyl substance determines the stability. Alkyl substance, alkyl group has to be hydrocarbons. It cannot be other halogens or header atoms. The other trend of the stability of the alkene is that when you have two alkyl substances, the relative stability goes from trans, which has the two substances on the opposite side of the double bond, is more stable than the cis, when you have two alkyl substances on the same side of the double bond, and that's about the same or a little bit more stable than two substances on the same carbon. So in general, let's summarize this. The more substance, the better. When you have the trans, is going to be more stable than cis. Let's take a look at one example question. In this review problem, you're going to see you're given 5 different alkene group double bonds. Now, if the question asks you, put them in order from low to high, if you take a pause here on the video, see if you can figure this out on your own before you look at the answer. Now, the lowest stability will be D, which has 1 substance. The highest stability comes to compound C, which has 4 substances. Now, after D, the second lowest one will be E. Now, notice that between E and B, they both have 2 substances. But B is trans, E is cis. So cis is less stable than trans. Even though B is trans, but it only has 2 substances, which is less stable than A, which has 3 substances. And of course, A is less stable than C, which has 4 substances. So the most stable is C, second one is A, and then B, and then E, and D. And since the question asking from order from low to high, so it's going to be D, E, B, A, C.